All right, so back to recording. Let's start the session. So our last scheduled MRI physics session of the fall semester. Today we're going to kind of dive into 3 different MRI techniques that are sensitive to motion or flow in some way. So they kind of fit together into a nice package. Preparing these sessions, I always feel like we're really only scratching the surface of these techniques. So hopefully everybody gets something out of it, but there's a lot more to learn. And really, in these sessions, I really just set out to give everyone who attended kind of the fundamentals and some basic understandings, which will set you up well to dig into the techniques that are most relevant to you further. But if there's something that I don't cover, as always, just ask me a question and I'll be happy to deviate. Just depending on what people want to know about. I'm always happy to slow it down and cover stuff in more detail. So from left to right, we're going to go over diffusion-weighted imaging first, and then sometime around the break, we'll jump into fMRI and end with arterial spin labeling. So let's just get right into it, because I don't have a whole other session where I can make up time if I ramble too much this one. So diffusion-weighted MRI first. Last session we were talking more about T1 and T2 weighting strategies, and also covering a little bit about how we image quickly, so things don't take forever. And diffusion-weighted imaging, generally we can think of as a T2 weighted sequence, but the technique is designed, or it aims to measure the diffusion of water, which I imagine you could have guessed. Diffusion of water. And the way that we do this is to actually encode additional phase information. So I will add that jot note as well. And then there's kind of the reason that this phase information is useful is that when we reverse it, we can get kind of a gauge of how molecules have moved during the time between encoding and reversal. And we'll kind of break that down pictorially here. But first, I want to talk a little bit about what diffusion is. Diffusion is just kind of random motion. It's technically called Brownian motion. I guess I'll just kind of add that in brackets here. Brownian, like the name. And this is different than flow. Flow of liquid, like in your blood vessels, or a fan blowing air around the room. Flow has kind of a net bulk motion of a substance. So your blood, is moving in a direction through an artery or a vein, generally. Whereas diffusion is just random movement. There's no net displacement or net movement of like the tissue body over time, the water body that we're talking about. And at any given point, a molecule of water, such as these ones, the blue, green, and purple water molecules that I've got here, they have an equal likelihood of moving in any direction at any given point. I'm just going to move these molecules over. So what that means is kind of the way that we imagine water diffusion to look. If I just draw some quick little trajectories here, for the blue one, maybe it wobbles upwards and then kind of heads downwards and ends up moving something in this direction. It's kind of a silly exercise, but I'll just kind of complete it for the 3 of them. So the green one ends up moving kind of in the same direction, or southwest direction, let's say, and the purple one ends up going kind of randomly this way. Who knows? There's no rhyme or reason to how these molecules move, but the point of this is that each of these molecules is moving on its own. They're acting kind of independently, and they have a a random probability of moving in any direction at any given point. So if all the molecules in a body of water that we're interested in are doing this, there's no net movement of the tissue. It's just molecules doing their own thing, vibrating and wandering around, having a good old time. This, I think, can also be referred to as a random walk, which is kind of more of a mathematical way of defining Brownian motion. And if you read more about diffusion-weighted imaging, you'll kind of get into these concepts more and more. Really, today we're just going to talk about how this applies to the diffusion tensor in diffusion tensor imaging in DTI. But it's the basis of diffusion-weighted imaging, is you expect molecules to be wobbling around. So in terms of how we actually encode and reverse phase information for diffusion and how this works, I've got a little diagram that I set up beforehand. So let's talk about a situation where there's no motion first, which is that green heading on the left here. What I've drawn is 9 spins, 9 hydrogen molecules, 3 times. So there's 3 3x3 grids. Just to belabor the point, there's this one in step 1, there's the middle, step 2, and then there's the third one, step 3. And let's kind of talk about the phase of these spins as we go through. So imagine this is post tip into the transverse plane, right? In time point 1, we haven't encoded any phase encoding, or we haven't run any phase encoding steps. We haven't encoded any phase information. So all of these molecules, I'm just going to have them kind of pointing upwards, all at the same phase in their precessional cycle. And in case it helps anybody, I'm imagining these guys to be cycling clockwise. So we're kind of looking at them top down. Hopefully that's kind of ringing a bell. And then if we encode some phase information here, that's what this kind of drawing of a gradient is. You can see that I've oriented the gradient from bottom to top of the page here. So like this, with the positive lobe on the top row and the negative lobe on the bottom row, roughly. That means that at time point 2, after this phase encoding gradient has been applied, we will have the top row ahead in phase of the middle row, and the bottom row is behind in phase. Again, imagining these things are cycling clockwise. And yeah, I'm just kind of like moving to a pretend situation in the future where the middle row has completed a couple full revolutions, whereas in that time, the top row has processed further, bottom row has processed less far. So it's behind in phase. Hopefully this is all ringing a bell. Then what we're going to do is apply a 180-degree pulse, RF pulse here, for the purposes of collecting a spin echo, which hopefully rings a bell. If not, we'll be kind of breaking down the spin echo pulse sequence, I think, next, or possibly in 2 little slide things that I've got here. But for now, we're doing a spin echo, and that means we can apply the exact same gradient to reverse our phase information. So that's what's happening in between step 2 and step 3. We have that exact same gradient, and it's going to reverse our phase information for us. That's because in spin echo, when we do that 180-degree pulse, the top row, which was ahead in phase, is now going to be behind in phase, and the bottom row switches as well. So I'm not going to draw that out, but that's kind of the reason for the 180-degree pulse. And as such, once we reverse or apply that second phase encoding gradient, if we're going to reverse all of our phase and have everything back at the same phase of its precessional cycle, right? So no molecules have moved, which means we haven't lost any signal. And when we collect this echo, all of our spins are going to be coherently in phase, and we're going to get that nice large echo of signal to acquire. Now let's move on to a more realistic scenario where there is motion of molecules during our scan. So I haven't drawn any motion in step 1, so I'll just add some arrows here to show everything's in phase. And then we're going to encode some phase information in our diffusion direction of interest, which we'll talk about it a little bit later. That'll mean this top row, again, is going to look the same because I haven't drawn any motion yet. We still got a 3x3 grid. So from top to bottom, ahead, reference, I guess, and behind in phase. And here I've drawn some blue arrows where we've got water molecules diffusing, right? So that means, let's circle in green. This spin, for example, is moving. It's diffusing from the top row in this example to the middle row with that little blue arrow denoting that. Get rid of this green here. Whereas there's another spin that's moving from the bottom row all the way to the top row. And then I just added a third diffusion step where a spin on the bottom row moves to a different location on the bottom row. All right, so 3 molecules are moving now, and we're going to do our 180-degree pulse. And we're going to reverse our phase encoding and assume that this diffusion has taken place before the reversal of phase encoding happens. So what's going to happen here is the molecules, I'll just draw them out, that haven't moved are going to have their phase that they've accumulated, whether ahead or behind, perfectly reversed. So they will stay in phase. I think I wanted this one to be, so this one hasn't moved. And I'm going to say this one hasn't either. And then this bottom row spin also hasn't moved. There's 3 molecules that have moved. All right, so let's address them, starting with the top one. So the spin on the top, sorry, I'm just kind of thinking while I talk here, never a good idea. This spin on the top that I have circled in purple here, it started on the bottom and now it's here. So it was behind in phase, then there was a 180-degree RF pulse, which means that that spin became ahead in phase. And now that it's on the, sorry, I just had to pause because I was evaluating my example diagram, which I think I've got wrong, and now I'm going to have to think through it, which is fine. So it was on the bottom row, it's behind in phase, 180-degree pulse puts it ahead in phase. Yeah, and then we've moved this spin up to the top row, where it's going to experience more positive phase encoding, which means the spin is going to be kind of even further ahead in phase by the time we reach step 3. Sorry about the pause. I've got it drawn behind in phase in my example diagram, which is definitely incorrect. So this top spin has become even further ahead in phase thanks to imperfect, reversal of its previous phase information that it had encoded, or that we had encoded into it. Then we've got the spin in the middle, which was ahead in phase. It got flipped to behind in phase. And we're considering this middle row to be kind of neutral in terms of how we encode phase information there. So nothing's going to change about this middle spin. It's going to remain behind in phase. And then we've got the bottom row spin, which just moved kind of from left to right. So it actually stayed in the correct location along our diffusion gradient that I've drawn in purple here to have its information perfectly reversed. So it ended up, it's behind in phase. It got 180-degree flip, so it's ahead in phase. And it's in that negative lobe, which is going to slow it down and cause that ahead of phase to be reversed and put it back in line. All right, so hopefully that makes sense. The result here is that we've got 2 spins, this one and this one, that are not in line with all the others, right? And that means that the difference between our no encoding net or echo, I guess, or NMB, and our with diffusion example NMB is we have a loss of signal due to diffusion in the diffusion case, the second example that we've gone through. And that is essentially what we're looking for. We are looking to encode phase in a given direction that we want to check for diffusion in, and then we're going to perfectly reverse that phase for spins that haven't moved, but for spins that have moved, they're not going to be in the same location where the gradient magnitude or amplitude is going to perfectly match the amplitude that they experienced initially, which is going to cause those spins that have moved to be out of phase coherence in at least to some small degree or large. And as a result, our echo is going to be smaller. We're going to see a loss in signal due to diffusion. And it's important to note that this only matters if water molecules diffuse in the same direction that our gradient is being applied in. So we saw that we had two spins that changed rows in this example. These two changed rows, and they, as a result, saw a different gradient amplitude than they did in the first place. Whereas this spin that moved just from left to right, in terms of its experience of the imaging gradient or the diffusion gradient, nothing changed. So we actually don't detect diffusion in directions orthogonal or other than the direction of the diffusion gradient that's actually being applied here. And that's pretty important. So that is essentially the concept of how we check for diffusion in a nutshell. And that's diffusion-weighted MRI. So let's talk about how this concept is applied. The main takeaway here, I'm just going to summarize in a single note. So we'll say, thanks to diffusion of water, when we encode and reverse, oh, that V went horribly wrong. We encode and reverse phase in a given diffusion direction, or a chosen diffusion direction, I suppose. We observe a decrease in signal. Maybe this is ringing alarm bells with the whole SNR conversation we had last session. If so, you're on the right track. But yeah, that's kind of the summary of diffusion-weighted MRI. So in terms of how this looks in a pulse sequence, we'll dig into that before we talk about these phase encoding details in greater detail. I'll keep that the same size. For the record, this is the only pulse sequence that I've got planned today, just to give you guys a refresher on spin echo, which is relevant for diffusion-weighted MRI. The other ones we could talk about, or we could break down fMRI and ASL. I figured it might take too much time. So here is our reminder of what pulse sequence diagrams mean to us. So you can see here on this pulse diagram, I've added a sixth line as if we needed any more, right? The diffusion line or diffusion gradients. So how does that play into this pulse sequence? I'm just going to kind of start drawing and talk through it as I go. So we're going to start with a 90-degree pulse here, which may actually happen in diffusion MRI because we're worried about low signal, because we're causing signal loss to measure diffusion. So we want to maximize, signal available in the transverse plane to record our echo. So we've got a 90-degree pulse here. We've got our slice selection gradient to match to make sure that we're only interacting with one slice of tissue that we're interested in. And then the next thing we're going to do is add the first of our diffusion gradients, right? Which I'm going to draw just as a good old rectangle here. And we're going to wait a certain amount of time to allow for water diffusion to occur. Essentially, the longer we wait, the higher the probability that any water molecule will have moved from its original location, because water molecules are always moving, but they need to move in the diffusion in the same direction as our diffusion-weighted gradient in order for there to be a imperfect reversal of phase information, and they need to move far enough that they actually see a significantly different amplitude of that diffusion-weighted gradient. So we're going to wait a certain amount of time in this pulse sequence diagram. Then we're going to apply a 180-degree pulse. And we're going to wait the same amount of time, balance on the other side, and apply our second diffusion-weighted gradient, which should be the exact same as the first one. It's just going to be roughly for the purposes of this diagram. Close enough. And let's need more space to the right. So I'm just going to redraw this 180-degree pulse kind of a little bit more balanced. All right, I'm going to try one more time and then stop being a perfectionist. Close enough. So that 180-degree pulse is supposed to be in the middle of those two diffusion gradients. And then once we've done this encoding and weighting and reversal process, then we have probe diffusion, and we can acquire our image and see how things have changed. So just to kind of briefly summarize that, I need an orange. So we're going to do maybe a negative phase lobe first to get us down to the bottom of K-space, and then we're going to do a positive one accompanied by a readout gradient. I'm actually just going to draw one at a time. Get rid of these dots. So we've got our phase encoding gradients that are ongoing, and we've got a matching set of frequency encoding gradients that look something like this. They should all be the same length. You can see I squeeze them together to fit more on the page. In terms of how this looks in K-space, everyone's favorite thing, I'm just going to draw a mini one so that I can mention that this is an echoplanar imaging sequence, like U to be black. Oh yeah, and I can draw some echoes here as well, which is the completion piece of this pulse sequence diagram. I think as we've gone on with this course, my echoes have become worse and worse. But oh well. Hopefully by now you know what they actually look like, so you don't need to rely on my drawing skills. So in terms of how this looks in K-space, what I've done here, I guess we should have a negative phase encoding lobe or frequency encoding lobe there as well. We start in the middle of K-space. We're going to move down to the bottom left thanks to that first negative phase encoding lobe and frequency encoding lobe. Yeah, we'll get rid of this one, just so that our trajectory actually makes sense. So we have our negative lobes to move us down in K-space, and then we're going to move, thanks to that first positive frequency encoding gradient lobe, we're going to move across K-space on the bottom to acquire our first echo. Then we're going to pop up in K-space thanks to that phase encoding positive lobe, the gradient there. And we're going to move all the way back across K-space thanks to our negative frequency encoding gradient there, and so on and so forth, right? We're kind of snaking across K-space and acquiring our echoes like this. And that, of course, would continue to the top of K-space, right? And this, yeah, like I mentioned, is a classic echoplanar imaging sequence. This is kind of EPI, as it's called. Just write it out here. This is a really important technique for DTI, fMRI, and ASL, because it's one of the quickest ways of acquiring your whole K-space, the amount of K-space information that you need to reconstruct an entire slice of an MRI image as quickly as possible. And we want to collect our diffusion-weighted slices very quickly, because for one, we are seeing a signal loss because of this whole diffusion thing that we're intentionally bringing out or drawing out of our images. So there's less signal available. And the longer we wait, the more T2 decay decreases our signal, right? It goes quite quickly. So we want to acquire all of our echoes as quickly as possible, but not take so long that our DTI sequence alone is going to take like a half hour or something. We still want to be reasonable, but balance SNR. And also the longer that we sit around in this K-space acquiring data, the more time there is for water diffusion to occur to an even further extent, which will kind of exacerbate the phase differences that we see in our later echoes that we're acquiring at the top of K-space if we're going from bottom to top. So and there's a few more technical reasons that I'm not going to go into here that have to do with chemical shift and air or like differences in phase due to the air cavities in your head. So there's other concerns about acquiring multiple lines of K-space, but essentially the quicker you do it, the more signal is available, and that's where we're kind of going to leave it for now. But this is essentially what a diffusion-weighted imaging sequence looks like. It's a classic spin echo sequence, but with this added line in the pulse sequence for diffusion. And I just want to mention this diffusion-weighted line. In reality, it's a combination of our Z, X, and Y gradients, right? So the slice selection gradient coil creates magnetic fields in the Z direction, bottom to top of the head of the body. The phase encoding is conventionally in the Y direction, and frequency encoding is in the X direction. So in reality, this diffusion line is a combination of all three of these coils, and the amplitude of the field they create determines our the vector that describes our diffusion weighting direction. So if, for example, we wanted to acquire or probe diffusion in the Z direction from bottom to top of the body, these diffusion weighted gradients, let's see if I can just move them, would just be up here, right? They would actually just be gradients that are applied along the Z-axis. Also, this is a good reminder that I have not drawn our second slice selection gradient, which definitely exists, I promise. So just to kind of balance our 180-degree pulse as well. So those diffusion-weighted gradients actually exist as a combination of our other three lines of gradient coils that physically exist in the MRI machine. But I like to kind of draw it on its own line, and I feel like that's fairly common in textbooks or resources that you might see, just to kind of isolate the precise timing and kind of visualize diffusion more clearly than like small gradients on the Z, X, and Y plane might do for you. It's also kind of easier to visualize the timing, like I said, than if they're mixed in with all the other gradients that are dealing with phase and frequency encoding for our actual image acquisition. So that's worth noting. And now we're going to kind of dig into diffusion weighting. But this is kind of the basics of how you collect a diffusion weighted volume. You essentially use spin echo with an extra gradient thrown in there to encode additional phase, and then reverse it and see how your signal changes. While we're here, it's worth noting that this is a change in signal from some reference state, right? So this is for a diffusion-weighted volume. But in order to actually see, how much signal you have lost due to diffusion encoding in a given direction, you need to collect a T2 image that's exactly the same, but doesn't have these diffusion lobes or gradients, right? So you have a reference state of just the brain in the exact same conditions that you are acquiring your diffusion-weighted volumes. And then when you actually acquire a diffusion-weighted volume, you can see what the change in signal is from reference to diffusion-weighted. And then you can kind of judge how much water has moved in a given region thanks to that comparison. And that's referred to as the subtraction method, where you just have, reference state minus active state or diffusion state in this case, and you look at the difference between those images. That's going to happen that's going to come up in fMRI and ASL as well, that subtraction method. But let's talk a little bit more about our diffusion gradients to kind of drive home how they actually function and how we determine our sensitivity to diffusion. So I'm just going to draw out our two lobes here a little bit larger and say there's a couple key features of our diffusion gradients. So in the middle here, there's a 180-degree pulse. It's not going to be drawn on the line here. But the time, from the start of our first diffusion gradient to the end of our second or reversal gradient should be balanced, right? So this distance in the drawing should be the same as that distance. Okay, so key factors in these diffusion-weighted gradients. There are a couple to consider. The first one is the amount of time that the gradient is actually on, right? That kind of gives you a sense of how much phase encoding you are, doing to your spins, how much phase you are actually encoding into your spins in that given direction. And that is classically referred to as small delta. Hope you all like Greek, or the Greek alphabet, because we're going to be using a little bit of it right now. The second time that matters to determine diffusion sensitivity is big delta. And that is the amount of time that you allow diffusion to occur, classically defined as from the very beginning of when you start encoding phase information to the beginning of when you start reversing that phase encoding information. That's essentially describing how much time you are allowing water molecules to diffuse. So essentially the amount of time that you're allowing for water molecules to move along that diffusion gradient direction and actually, imperfectly rephase and become incoherent for a signal acquisition. And the third factor that matters here, I'll draw on the left one again, is the amplitude of your diffusion-weighted gradient, which is a big G. And all of these things come together in an equation that I'm not going to draw out here. We definitely can. It's not that complicated, but I don't think it really matters until you're defending, and then you're going to need to look it up anyway to remember. These factors all come together in something called the B value. So if you've read or are familiar with diffusion-weighted scans at all, you will have come across, B equals 1,000 or 2,000 or 900, what have you. That is a number that's describing the diffusion sensitivity of your scan. And like I just kind of drew out, it depends upon diffusion time, which is our big delta, and diffusion gradient amplitude, and duration. Oh, sorry, I should have added a G here to be consistent. And then this is our small delta. So let's kind of break down why this would be the case, just to kind of drive it home. Hopefully everybody's following. First, focusing on diffusion time, as I've already mentioned, but just to kind of write it out, the more time you wait increases the probability because remember, diffusion is a kind of a random process. So the probability of water molecules diffusing or moving along that direction of interest. It's not my best spelling, not my most readable text. All right, and then the other two factors kind of come together in terms of the gradient we're applying. So I'm going to talk about them together in blue. So these two factors, we've already kind of talked about, time and the likelihood of movement. These two factors contribute separately in that they determine how much phase is encoded for spins along that diffusion direction, right? So together, if you think of kind of like the area under the curve of this diffusion gradient, the area of that box is its length times its height, its duration times its amplitude, right? And the more areas under there, the more phase information you are encoding. So in that way, if we increase either of them, we're encoding more phase, and more phase encoding, what that means is that diffusion of an increasingly smaller distance actually matters. So, okay, so diffusion of an increasingly smaller distance results in imperfect rephasing. And that's kind of why these two factors matter. The concept here visually is if we have a gradient like the one I drew before that has kind of like a gentle slope, we'll say, versus a gradient that's much more powerful, applied for the same amount of time. If, for example, a spin moves from this slightly negative location, or this moderately negative location, to, it moves slightly upwards or slightly downwards, it's going to see a gradient that's similar in amplitude. If we're looking at kind of, this length here, those two lengths, those tiny red lines that I drew, are pretty similar, which means that for the most part, that spin is going to be rephased, semi-perfectly, like close enough that it's going to be in coherence enough with the rest of the NMB to contribute to the echo in a meaningful way. So essentially the decrease in signal that you're going to see from this small diffusion is pretty minor. You won't really be able to see it very much on your image. And maybe it would just be misinterpreted as noise, which is intrinsic to MRI imaging. Whereas in the same situation, here to here, in this more powerful gradient, so this would be a larger G, a larger gradient amplitude in that drawing I've got at the top of the screen. Here, the difference in magnitude of gradients that this guy sees is more substantial. See that I've kind of drawn it a little bit taller than the other one, but to make it more similar, let's say it's like here. Close enough. You probably get the idea that these lines are significantly different in length, so there's going to be a less accurate reversal of this spin's phase, and that means you're going to see that signal loss in your image, essentially making you more sensitive to diffusion across small distances. So diffusion time will give you kind of increased probability of water moving far enough along the gradient, whereas modifying the gradient itself will kind of determine how far a water molecule needs to diffuse before its phase is kind of not reversed correctly and results in signal dropout. So there's kind of two ways of encoding diffusion weighting in your images. Rule of thumb, if you're kind of considering DTI or diffusion weighted images, a b-value of like 1,000 is pretty normal. I would say the range is probably closer to like 750 to 1,000. The units don't matter to us here, but they're seconds per millimeter squared. So that's pretty normal for a diffusion weighted scan. It's kind of the range you would expect to see for a classic one, and that's kind of the standard for diffusion weighted imaging. Whereas scans with b-values of, well, I don't know, somewhere between 2,000, 3,000, or even up to like 6,000 or so. Those are much more sensitive to diffusion, I would consider like high sensitivity these days on 3T scanners. And they'll, of course, be more sensitive to diffusion in small distances, but result in much less signal available. So you need to compensate typically with something like higher field strength or larger voxels or that kind of thing to make sure that you're still outweighing noise in your signal to noise ratio. But just to give you a rule of thumb for what kind of diffusion weighted image you're looking at. the last thing here is that technically, this gradient that we've got here is not perfectly rectangular, which means that there's like these ramp up and ramp down periods in reality for gradients, so they're more like trapezoids than they are rectangles. But the b-value equation assumes that our gradients are rectangular. So generally it's, worth just drawing them like rectangles, even though in reality there are these periods where, increased, or like power is increasing through the coils and they're ramping up to their gradient amplitude. I mentioned this because it was a question I actually got at my defense, so it might be relevant if you actually need to describe how diffusion weighting works. In reality, your gradients are trapezoidal because there's these like increasing power and decreasing power periods, but the actual b value itself relies on the assumption that gradients are rectangular. So you just kind of ignore those triangles to either side of the rectangle here. So that's diffusion weighting, and that's how you determine kind of how sensitive your image is going to be to diffusion. Now, what does this actually look like, right? The reason that we're all here. On the left, there's an example of a T2 weighted image. It is a lower resolution than T2 weighted images we've seen in the past because we're matching the resolution of our diffusion weighted volumes, which need to have larger voxels and larger slice thicknesses in order to actually obtain enough signal to outweigh noise. And I will note that this still is probably pretty gray on your screen, and I apologize for that, but I had to increase the contrast of the right volume quite a bit to even get it this bright. So there's a lot less signal available in our diffusion weighted volumes. And this one, so this is a, let me just draw it here or write it down here. So this is a B equals 900 scan. So in that normal range, and already there's quite a bit of signal dropout. Now I've drawn these arrows on here to highlight my guess as to the direction of diffusion that has been encoded in this image. And I'm guessing this direction, it could be, I think it is, front to back and slightly lateral. But it also, it could be in the other direction. That circle over here is depicting that I think it's coming out of the page, but it could just as easily be going into the page, or it could be more lateral than I would have guessed. The reason that I'm guessing here is because I didn't want to go look up the table of vectors in this 30 volume scan to figure out which one this was. It doesn't particularly matter because we can still, regardless, highlight changes in the image that are going to kind of help us understand what this is actually telling us. So let's look at 3 different regions of our image. First, I want to highlight the ventricles. So this one's bigger, so I'm going to highlight it in blue. In our T2 weighted reference image, the ventricle is bright, right? Because there's a lot of signal left there. There's lots of water. T2 is longer in water, so we get lots of signal from the ventricle. Whereas in the exact same brain, just a few seconds later in a diffusion weighted image, the ventricle is, almost completely dark. And in fact, it should be, as black as the outside, essentially, maybe a little lighter, but there's, you might be able to see some kind of like intermittent gray areas in the ventricle. That is definitely noise. The reason, so, okay, let me start writing stuff out here. So in our T2 weighted image, which I've got in green here, the ventricle is bright. And then in the diffusion coded image, the ventricle is very dark. This is because there is nothing standing in the way, aside from the sides of the ventricle itself. There's nothing standing in the way of water molecules just moving away, just going off to do their own thing during that diffusion weighted, or during that diffusion time, before that time between the encoding and the reversal gradients. So signal in CSF is lost quite quickly because water is free to move, and move it does. Whereas in something like the corpus callosum, which I'm going to do in orange. So let's just look at the front of the corpus callosum, the genu. If you're not familiar, this is like the main connective tract between your hemispheres. In the brain, it's proceeding most of its fibers from left to right. So in our T2-weight image, it's kind of a dark gray because there's, T2 is kind of faster in fatty tissues, so a signal is lost there more quickly and becomes gray in our T2-weight image. Whereas in the diffusion-weighted image, it's actually, lighter. It's certainly lighter than surrounding tissues like the ventricles, which is more important than it being lighter than the T2-weight image, because these are not on the same contrast scales. Like I said, the diffusion-weight image is a lot darker, so I need to brighten things up. So it doesn't really matter that our tissue here is lighter than the reference image, because in reality, if you look at these two side by side in the same contrast window, the whole brain of the diffusion-encoded image is darker. But what this is telling us for the GNU, this lateral tract, essentially is because it's brighter in the diffusion-coded image. Just going to say it's dark gray here. That means that there has been less diffusion in that tissue than in surrounding tissues like the ventricles and like the front to back tracts that we're going to talk about next. And the reason for that is because there's stuff in the way, right? If we're looking at diffusion across the GNU, in this kind of direction, there's a whole lot of axons, as I just kind of rotate my tablet here, that are roughly running this way, right? And axons have cellular membranes. They're fibers, like little tubes or straws, connecting your neurons and allowing you to think and process information in interesting ways. And because those cellular membranes are, very commonly oriented from left to right in the brain in the GNU, that means that water might, try to move this direction, but bump into a cell membrane and not be able to diffuse further. So there's kind of less diffusion that's occurring in that direction in the GNU. And that results in more signal left because there's less signal lost to diffusion in our direction of interest. And then finally, if we look at the tract that's connecting, back to the front of the brain, something like this, let's say it's the SLF. This is an area that's darker. I feel like I've drawn a little bit too close, so it's hard to see the difference. Let me just make that a little bit larger. You can see this kind of darker line in that circle that I've drawn surrounded by lighter gray tissue. And this is kind of highlighting a tract in the brain where water is kind of more free to move in this direction. I shouldn't be drawing this in blue. This is going to get a little bit confusing. But water is allowed, there's less restrictions to its diffusion in the direction of interest, that purple arrow that I've drawn on this image, because axons in this region are oriented from front to back here, or back to front. So there's more likelihood that water is going to be able to move in that diffusion direction just because of the way that axons are oriented, and that is resulting in a darker region of the brain. I just kind of undo all these arrows that I drew. So the tract there is darker because more signal has been lost to diffusion, right? So this is probably the SLF. I'm just going to say it's front to back. Should add that to the GNU as well. And here we see a dark tract because water is more able to diffuse in that direction. So let me just firm up these side to side. And then similarly to the corpus callosum, the contrast between our images doesn't matter too much just because of those different scales like I talked about before. But you can see that that same tract is kind of fattier tissue, so it's darker than the ventricle in the T2-weight image, but it's highlighted a lot more when we can look at diffusion along the direction that we expect that tract to be oriented. Right. So one more thing about diffusion-weighted imaging, and we'll take a quicker break and jump into functional MRI to make sure we get there. So the last thing to talk about with diffusion-weighted imaging is the tensor. DTI is something people are much more likely to talk about than diffusion-weighted imaging, or DWI, and that's because DTI is so common. And the idea here is, so far we've been talking about diffusion in one direction, right? From front to back or bottom to top or something like that. But that only gives us information about water movement in that direction and no other direction. So it's not that useful when we are considering well, we want to understand water diffusion in the brain, because like I said, water has that, or in diffusion conditions or diffusion motion, water has an equal likelihood of moving in any direction unless those barriers exist. And if we're able to quantify, how much diffusion we see in any given direction, we can kind of get an idea of where barriers exist to diffusion, and that lets us investigate white matter in the brain. Or muscle fibers. It's another way that diffusion-weighted imaging is used, because fibers are also highly coherent. Muscle fibers are very coherent in how they're oriented. So the concept here is, if we have a point in the middle and we're measuring diffusion in many different directions, we're going to see kind of different magnitudes of these vectors, or different amounts of signal, and essentially the magnitude of these vectors. So zero magnitude, this is representing the amount of signal loss. And if we do this in enough unique directions, and of course drawing in 3D is never amazing, but just coming to like the outsides of this sphere, if we kind of probe enough diffusion directions, we can start to get a sense of the size and shape of this ellipsoid, this three-dimensional oblong sphere that I've drawn, this ellipsoid. In this case, where water kind of can move wherever it likes, and all these arrows are pretty large, we might be somewhere in like a ventricle where water is kind of free to move in any direction. But in white matter or muscle fibers or what have you, you might more often see tensors that are like this, where they're pretty stretched. And diffusion, signal loss is quite high when you're measuring in the primary direction of diffusion in an area, and quite low when you're measuring kind of the perpendicular dimensions of that ellipsoid. So looking at these differences, you're able to have some interesting information about the brain, because, or just tissue in general, because the only thing that's stopping water from moving in a certain direction is barriers like cell membranes, which in the brain I have mentioned commonly axons, where instead of being able to just diffuse wherever it wants, water might wander this way and then bump into the cell membrane and have to go back and then bump the other way and that kind of thing. So it's eventually this water molecule is going to be moving, it's more probable for it to move in this top to bottom orientation than left to right. And that would result in a kind of stretched out tensor. And there are lots of interesting measures we can get from the tensor. I haven't really talked about measures in other imaging sequence, so I'm going to kind of avoid talking about them for DTI as well, since we're just really talking about the basics. But they're really good ways of breaking down kind of the structure of these membranes, and the more membranes there are, the more stretched and elongated this tensor gets, and that can kind of tell us about how much stuff is in the way of water diffusion. And in something like white matter, we can talk about like, okay, well then how much myelin is on those axons, how many axons are kind of closely packed together, because factors like that increase the amount of diffusion restrictions that we see. So that's the diffusion tensor. In order to actually collect it, we need to probe diffusion in many directions. So at minimum, you need at least 6 directions of diffusion measured. I forgot to draw or to write a 6 in there. Okay, great. So at least 6 directions must be measured to construct the tensor. But commonly, there's like 30 or so directions of diffusion that we measure. And that's kind of to increase the accuracy of the tensor that we are reconstructing. So with 6, you really only get the primary directions of that ellipsoid, both positive and negative. So just like basically your axes, right? X, Y, and Z axes, both positive and negative, that's 6 directions. But that doesn't really tell you as much information as measuring, along the diagonals does. This is obviously going to be very messy, but essentially the more arrows you draw, the more complete and accurate an ellipsoid you can draw, right? Because you're collecting more points along the outside, so you can kind of better represent the overall diffusion conditions in an area. This is obviously very important when you have more than one population of fibers of some kind crossing, which is very common conditions to measure diffusion in, where the tensor kind of breaks down a little bit. You need to collect more information to more accurately model those scenarios. And the last thing on tractography and diffusion tensor imaging is all these images that you see of the brain that are kind of these like actual tracts of fibers that are connecting one region to another. And you can see the same thing with muscle fibers or cardiology, like imaging of the heart, angiography, that kind of stuff. Well, angiography is, I suppose, measuring blood vessels, which is different. But anyway, if you're measuring fibers, you can use these tensors to kind of connect the dots and figure out where tracts exist of some kind of tissue. So in this way, you can run any kind of tractography algorithm using these tensors. And the way that that works is essentially you start in one voxel, let's say this bottom one, and there's a primary orientation of the tensor in this voxel. So what you do is you take a step in that direction into another voxel, usually. So maybe we're going to step like a millimeter or two, and we end up in this voxel at this location. And now we look at the primary diffusion direction again, which now is actually just straight up. So our tractography algorithm, we take another step straight upwards, and we're in the same voxel, so we do the exact same thing, straight upwards. And now here we're in a voxel where the diffusion tensor is oriented kind of more up and left on the screen. So we're going to step up and left and then do the same thing and wander out of this voxel to the next one. In this scenario, I'm drawing the step sizes such that they are smaller than our voxel size. That's why we see 2 steps in the same voxel. That's kind of better practice because then you don't skip any tensors that you might be missing. But the result of this method of just connecting the dots essentially, or following the path that the tensors lay out for you until you reach some threshold of diffusion tensor thickness or size or something like that, that causes you to stop doing this this process, you can kind of connect the dots and presume that's where a tract of fibers is, right? And that's how you essentially go from a whole bundle or you can construct like a whole brain bundle of these fibers, and then you can kind of break it down to fibers that are specifically connecting one region to another. That's all from just kind of following these diffusion tensors and just like taking their primary orientation to step in the next direction and assume that's where the fiber bundle continues. That's how you get these great images of the brain where you can actually isolate fiber tracts. In case you're wondering about the colors, on the left, we're looking at primary orientation of a tensor, where green is back to front and red is side to side and blue is bottom to top. It's kind of the normal convention in the brain. And then on the right, each tract is colored individually, so you can actually see different tracts that are connecting, temporal to frontal regions of the brain, or left to right side, or something like that. So that is diffusion-weighted imaging in as little detail as I thought was reasonable. Next up, we have functional MRI and maybe a little bit on ASL before we wrap up for the day. But since we're over halfway, let's take a 5-minute break and come back at 11:10 to talk about fMRI and methods sensitive to blood flow. Okay, so back to recording and on to fMRI. Just talked about tractography. Instead of looking at diffusion of water like we were in diffusion-weighted imaging, functional MRI, we're now looking at brain activity. But the way that this works is using the proxy of blood flow, as this has kind of like useful magnetic properties that we can use to infer brain activity. The concept here, I guess, is when your neurons are firing and generating their action potentials and working away, they are consuming resources, nutrients, oxygen, things like that, and the brain is increasing blood flow to those areas to provide enough nutrients for those neurons to continue functioning. So if we can get a sense of where blood flow has kind of changed in the brain, we can get a sense of where neurons are firing, or where neurons are active, what regions of the brain are active. That kind of language is used in fMRI. And the reason the blood flow is useful to us is because there is an important difference between oxygenated blood and deoxygenated red blood cells, or specifically hemoglobin on those red blood cells. I just kind of like writing RBC instead of hemoglobin each time. But when we're considering oxygenated hemoglobin, this material is diamagnetic, which we can break down for sure, whereas deoxygenated blood is paramagnetic. And I always get these backwards, so I need to look it up every time. Yeah, don't feel don't feel sad if you can never remember, like me, which of these is diamagnetic versus paramagnetic. Maybe by the end of this section, things will make a little bit more sense. What diamagnetic means, though, is that this material interacts with the magnetic field it experiences in an interesting way. Same with paramagnetic, but if we kind of just draw some magnetic field lines, like you might see, I kind of am just representing the strength of a magnetic field in an area. So, something like this. Actually, let me just kind of break this down a little bit for just quickly so that we know what I'm actually drawing here. Generally, a magnetic field is represented by these field lines that are describing the strength of the field at a given location. And these ones that are kind of asymptotic at the top and bottom that are kind of stretching away, those are just even larger, circles that we can't draw here. So this is kind of showing where it's like those geological topographical maps where there's lines that are showing elevation. Here we're showing magnetic field strength. So lines that are closer to the body are strong, and lines that are further away are kind of a weaker magnetic field, but still present. So I'm just kind of zooming in on one of these, sides, like over here, when I'm drawing this diamagnetic, paramagnetic stuff, to show just kind of some lines of a magnetic field that are passing over this red blood cell that we're interested in. And I'll just draw them on both right now. So we've got, what, 5 lines here? So just, showing that both of these molecules are experiencing a magnetic field. But then within the, the area of influence of this oxygenated red blood cell, the diamagnetic one, the field is actually going to be, actually, let me just redraw these lines to more clearly drive home what I'm actually trying to represent here. Okay, so these two or this one's more centered. Good enough. So if there were no interaction between the red blood cell and the magnetic field, we would just see kind of like these 3 field lines continue, right? It just wouldn't disturb the magnetic field. But because the oxygenated red blood cell and hemoglobin are diamagnetic, the magnetic field is actually weakened within that, the field of influence of that red blood cell. And it's the opposite for paramagnetic, where instead of those 3 lines passing through this area of influence where there's a magnetic field interaction, the magnetic field is actually, amplified, essentially. So instead of 3 lines, now there's 6 or something like that. So the magnetic field is kind of increased, or the paramagnetic material experiences an increased magnetic field compared to the field strength of our MRI, and oxygenated or diamagnetic material experiences the opposite. Now, this is very important because paramagnetic materials, they increase phase differences in surrounding tissue and other blood cells and water and spins, thus increasing dephasing. You know how we talked about T2 star effects? This is a T2 star effect, right? It's not just typical spin-spin interactions, it's differences in the magnetic field that are experienced by local tissues and their surrounding environment based on factors other than just interactions of spins and exchanging that energy in that paired way like we talked about in session 2 or 3. So the more deoxygenated blood that there is in a region, the more dephasing occurs and the less signal you can get from that region along that T2 star curve. So, the longer, compared to a region where there aren't paramagnetic materials, signal will decay more rapidly, just because there's increased dephasing in this region. Now, what happens when neurons are firing and blood is flowing to those areas is kind of convenient for MRI because although there is more deoxygenated blood being used by those, or being produced, I guess, by those neurons. Sorry, let me rephrase. Although neurons are using oxygen that's on that hemoglobin, and thus there's kind of deoxygenated blood in the area, our vascular system actually kind of overshoots and oversupplies neurons with blood just to make sure, that our demands of those neurons are met, which means that our blood vessels widen and more blood flows to that area, and there's actually an increased, ratio of oxygenated to deoxygenated blood in the area when neurons are active and blood is flowing into an area. So instead of neuronal activity increasing paramagnetic materials and decreasing signal in an area, there's actually an increased proportion of diamagnetic oxygenated blood, which results in an increase in signal from tissue that is having more blood supplied to it. So let me show you a little animation of what that looks like from the handy Amios website. We've got a neuron that's firing once it starts playing. Oh, sorry, I just realized I'm sharing my OneNote screen and not my whole screen. Let me just switch this quickly. All right, cool. So Amios. We have this neuron that's firing on the right. We have our blood vessel in the middle, and we have this ratio of diamagnetic in red and paramagnetic in blue hemoglobin. So as the neuron begins to fire, our blood vessel widens, and there's a lot more oxygenated blood that is supplied to that neuron, and a kind of a decreased proportion of deoxygenated hemoglobin, that paramagnetic material, and that is causing us to see an increase in signal from that region. So you can see it was covered up there. On the bottom, there's a kind of a time course of activity in the neuron and signal. You can see when activity begins, soon after signal increases as blood flow increases to that area. And this is something called this is the bold response or bold signal. It stands for blood oxygen level dependent. And that signal is essentially what we are leveraging in fMRI. Because we have increased diamagnetic materials, there's kind of less dephasing and an increase in signal in an area, which is very convenient. I'm just going to stay on my whole screen because I think we have some more animations. So what this looks like is, just to draw it out, I wanted a darker blue here. It looks kind of like an action potential. So you can see on these axes, I've got time in actual seconds and this percentage of change in signal on the y-axis. So if our baseline is 0% change, kind of the signal we would expect from a region, if there's a stimulus that's applied at the 0-second mark, which is what that red arrow is representing, soon after a couple seconds, oh, sorry, I want this to be thicker. Oh, maybe not, it's too thick. Nope, I did want that thing. Okay, cool. So we've got this line at 0, then there's kind of an initial undershoot followed by increase up to just a couple percentage points of increase in signal from an area. and after the stimulus, as blood flow is kind of no longer needed and the neuron isn't firing anymore, eventually the signal kind of decays back down. There's a bit of an undershoot, and then it stabilizes. So like I was saying, it looks a little bit like an action potential. There's kind of 3 phases here to highlight. There's phase 1, this initial small dip in signal, which is hard to detect and kind of not as relevant as this second stage of this ramp to the peak signal change, ramp to peak. And then there's this third phase of kind of decay and the post-stimulus undershoot. It just came to mind that I have a small mnemonic that helps me remember what the effects of these diamagnetic and paramagnetic things are. I don't know if this will help anyone else, so I still forget which, oxygenated and deoxygenated blood, what they do. Although now that I'm talking out loud, just kind of remembering that there's more oxygenated blood in an area helps me to remember that there's more diamagnetic material there because there's less dephasing in an area. I always think about how diamagnetic causes magnetic fields to kind of like die down and become weaker in an area, whereas paramagnetic is kind of like, pairing the magnetic field together and increasing its strength. Maybe a little bit silly, but that's, the memory, the life hack that I have to remember these things. So diamagnetic kind of causes the magnetic fields to die down, whereas paramagnetic kind of like, pairs it up and, I don't know, experiences a stronger magnetic field thanks to that interaction. So maybe that'll help somebody. And this is kind of the result of increased oxygenated blood. You see an increase in signal for a small amount of time, followed by a decay and undershoot and back to normal when blood flow stabilizes again. And this is just for a single stimulus. But it's worth noting here. Let me just write out. So bold at the top there stands for blood oxygen level dependent, which I already said. And I'm just going to kind of summarize here. Increasing oxygenated hemoglobin, which is diamagnetic. It lengthens T2 and T2 star, thus increasing our signal. And that is the basis of how we are detecting brain activity. We're looking at increase of signal based on changes in blood flow and using that to infer brain activity. It's worth noting that this is only a couple of percentage points of change, so it's easily outweighed by noise, and we can combat that, which we'll talk about a little bit later. But it's important to realize, I guess, that fMRI is susceptible to the effects of machine noise, which is intrinsic to MRI, as I keep kind of saying. And it's also worth noting that, as I've kind of drawn out here, this is not an immediate effect. The bold response can be delayed by 5 to 15 seconds commonly, depending on the region of the brain that you're interested in, kind of like the vascularization, the type of activity that's going on, the person that you're imaging, the scanner that you're using. Bold is very kind of, it's dependent on a lot of different things, and thus it's one of those phenomena or measures that's useful kind of within a subject and possibly between subjects, but not really as like a quantifiable biological truth so much, just because it's dependent on a lot of different factors. So it's better to think of it as kind of a comparison metric than a biological truth metric. And the same thing can be said of diffusion and many MRI measures. It's just kind of worth keeping in mind. I just want to write down bold response is often delayed. And that can be, between 5 to 15 seconds, and that's common. So you may need to be imaging for quite a while to actually capture this change in signal. Yeah, worth noting. Now, another way that you can kind of make sure that you are accurately detecting a change in signal due to blood flow is to kind of keep that blood flow increased for longer, right? So this is just for a short stimulus. Now we're going to try to draw an extended stimulus or stimulus train. So here I've got red arrows showing 6 stimuli. And again, this percent change on the y-axis in just kind of signal intensity in a region. And this is for like a 40-second time course. I'm going to give myself a little bit more space. All right, so what this looks like is now, because there's multiple stimuli, we can kind of think of this as multiple bold responses. This is definitely going to be a challenge for me, but I'll do my best. All right, let's choose a lighter blue. So if we have our first stimulus at 0, let's say our first bold response is at like 5 seconds or so, assuming this is kind of a quick response to the stimulus in this region that we're interested in. So we have this kind of initial undershoot and then this increase in signal up to maybe a couple percentage points, up to like 2 or so, and then this decay and undershoot. But then there's another stimulus presented at the 5-second mark, which means we're going to see another response at like the 10-second mark, right? And then kind of the same trajectory, and you get the idea. I'm just going to start drawing overlapping waves. That should all be pretty similar, but by this point, you probably know my drawing acuity, drawing abilities are passable at best. But then when we're considering the amount of signal that's kind of contributed by these overlapping and likely closer together, bold responses than I have drawn here, what we get instead is a kind of a net response that's larger and more prolonged than any of these individual responses. So we'll say it's drawn kind of like this. There's same kind of increase. Again, we're kind of like increasing the amplitude. I really want to just make sure you can actually tell the difference between my squiggles. So maybe these bold responses would be larger and closer together to actually sum to create this larger time course or bold response that's prolonged at the top. And then we have some kind of like wibbly wobbly stuff as our individual responses vary over time, but at some sort of plateau, right? And then after the stimuli have stopped at 25 seconds, 10 or 15 seconds later, again, there'll be this decay in signal and then an undershoot and return to baseline, essentially. So this is kind of what happens when we have a prolonged or a stimulus train. We get this plateau of increased signal, and now we can image the same region multiple times or multiple volumes to kind of confirm that we're seeing increased signal in a region, not just due to noise, which is variable and random, but due to a consistent increase in signal thanks to the bold response. So this is one way that we can kind of make sure that we're looking at actual blood flow instead of just noise, is extending our stimulus train. What did I write up here? I've got a note here about how bold is variable, so I will follow that out. Yeah, okay. I'll just keep it. So the bold response varies by subject, brain region, maybe even task or scanner, those more study design kind of issues. So it's worth keeping that in mind. Got a little animation here kind of showing some actual analysis of what this might look like. So here we're looking at time courses of signal in 2 different areas. The red voxel, which is in the motor cortex related to the thumb, and then a yellow voxel, which looks to be kind of in the inferior parietal or superior occipital lobe, which is not related to thumb function, right? So over time, as the thumb is moving, we see increased signal in the red voxel, and then no change in the yellow voxel. So when we compare this to kind of what we would expect in terms of our like task design and activity, we can conclude that the red voxel was, significantly activated during this thumb movement task, whereas the yellow voxel didn't have any, significant relationship to the activity time course. I'll just let this play one more time so you can kind of get a sense of what it means to see time courses of signal. And then, of course, we can see that before it's all smoothed out like it's being smoothed right now, the signal is quite noisy, just because, again, we're looking for differences in signal that are just, between 1 to 4 maybe % in the tissue or in a region. So it's easy for those to be outweighed by noise. And as a result, we're kind of repeating this task a couple times here to make sure that we're seeing an increase in signal instead of just an aberration of noise. Yeah, fMRI acquisitions tend to acquire thousands of volumes instead of just like the, one volume of the brain in the structural image, or 30, 35 volumes in the diffusion-weighted image. fMRI focuses more on kind of quick acquisitions, so you can see that change in blood flow on the smaller scale, and also acquiring thousands of volumes quite quickly, so that you can average them together and see that consistent increase in signal or no change in signal in the region due to the bold response or lack thereof, and kind of cancel out some of the noise that is influencing your images. And that comes back to that SNR discussion and the kind of like quiz we had last time, where if you average multiple images, noise can kind of cancel each other or cancel itself out a little bit. Okay, so this can result in activity maps, which is probably the most popular usage or visualization of MRI and fMRI in general culture, in the zeitgeist, is these brain maps where areas are lighting up like they're active. Of course, this is only referring to blood flow, and we're using that to infer neurons are active. It's a fairly reasonable assumption, but it's not just actually showing you where neurons are firing, unfortunately. But these can be quite informative. This picture that I just pulled off of Google looks to be a language task, assuming that brighter hemisphere is the left hemisphere. And you can see there's regions of the brain that are highlighted with this heat map. And what we have, the way that we get these is, again, the subtraction method to get these activity maps. So once we've kind of got a sense of what our reference state looks like, which is generally a T2 star weighted image, to just acquire it as quick as possible using gradient echo, we take our reference image, and then we subtract our active state, whatever that might mean, whether it's a thumb movement or this language task or whatever. And well, actually, I'm going to call this task just to kind of distinguish it from activity. Just some kind of rough termage there. Yeah, so task being whatever you're getting the subject to do. And then, what's left over that we've determined is not just noise and not a statistical false positive. That's our activity map of regions of the brain where we are confident that blood flow has increased, and we're confident that neurons were kind of active during our task. Of course, this is not always perfect, because you're doing this comparison of, was this voxel significantly activated by our task across generally the whole brain. So you can also get images closer to the one below, where if you don't necessarily use the best methods, you can find a lot of activation. You're doing this comparison, voxel to voxel across the brain of reference versus task hundreds of thousands of times. Generally an image of the brain, well, maybe, still hundreds of thousands if you're doing an fMRI scan that has like a 64 by 64 or 128 by 128 resolution, and that's how many slices, maybe like 30 to 50 slices of the brain. There's a lot of brain voxels in there, right? So you're doing a lot of statistical comparisons, and that increases your likelihood of false positives, which is something you need to account for in fMRI, of course. But this is not generally understood by media outlets. this is probably not news to anybody, but it is like I was looking for fMRI image studies just to show some activity maps like this that are kind of clear. And I found one that I couldn't help but click on saying, oh, we figured out what coffee does to the brain. Essentially, it creates a superhuman where the entire brain is more active. Thankfully, this study was from 2005, but it was just done with 15 people. And that's like not nearly enough for a reasonable conclusion in MRI in general, let alone fMRI, where you're doing even more comparisons and you need to do nice, intelligent modeling and processing to actually get meaningful results, which generally, if you see something that's more limited, like the one on top, I would consider that to be more reasonable than the one on the bottom where there's activity everywhere. But who knows? It really depends on the study. But yeah, you may see some wild stories out there from 2020. Even this kind of stuff still happens with fMRI, which is either entertaining or possibly, just motivating to teach people about how fMRI actually works. Depends on the person, I guess. Any other notes that I had here? Yeah, okay, so we've already talked about how voxels are easily influenced by noise. You need to collect many volumes to make sure that you're actually seeing like a meaningful increase in blood flow and signal, and false positives as well. All right, great. So let's move on to how you actually acquire fMRI images. I didn't want to draw another pulse sequence, as I mentioned before, so they take a little while. But I've got some rules of thumb for how fMRI is actually done. Similar to DTI, you want to collect your slices and volumes quickly, but even more quickly now because you have many of these volumes to acquire to do that averaging to see a meaningful fold response, right? You want to acquire thousands of volumes. So generally at 3 Tesla, fMRI is done with gradient echo sequences that are T2 star weighted. Although I learned that at higher field strengths like 7 Tesla and above, generally a spin echo is used to get just to kind of increase your signal available and move from that T2 star decay curve to that T2 decay curve. There are techniques that we didn't talk about in these sessions like fast spin echo or turbo spin echo that allow you to kind of speed up how long spin echo sequences might take. So it's not like there's a huge increase in time required for spin echo, but at 3 Tesla and below, generally it's gradient echo that we're using. And of course, just to have an actual note here, sequence choices are really a balance between S and R. So making sure the signal you see is meaningful, both your spatial resolution, so your voxel size and slice thickness, and your temporal resolution. Generally, you want fMRI scans to have high temporal resolution, so seeing changes on a smaller time scale than you would structural because you expect blood flow to change over time, whereas structure is structure. It doesn't change very often, in my experience. And things like subject motion, doing fMRI scans in kids, I can tell you, motion is common, especially when they have to stare at a blank screen or a cross. That is boring stuff for a child. So yeah, you really have to balance a lot of different factors to kind of come up with a compromise of an fMRI scan. Generally, I would say 2 millimeters to 4 or 5 millimeters. Slice thickness is reasonable. Although feel free to correct me if somebody thinks I'm very, very off pace. It's similar for DTI where 2 millimeters is kind of common. Higher than that and you are in good shape or have a nice scanner. And then resolution for fMRI typically like 64 by 64 in a slice or 128 by 128. Yeah, so that kind of resolution is to be expected in fMRI, just to make sure your voxels are large enough to capture enough signal to outweigh that noise. And like I've already mentioned, you might be collecting 1,000 or more volumes to get good time courses of signal and average volumes together to outweigh noise. The way I had this written was to isolate bold from noise. Okay, so we've talked about task design so far in fMRI, where you're getting the subject to do something like move their thumb or read a page or talk out loud, that kind of thing, to look at which areas of the brain are active. But I would say much more common these days is resting state fMRI, which is very interesting. The idea of resting state fMRI is rather than compare a reference image to a task image, what you do is you just collect a lot of volumes like usual. You're collecting on kind of like the millisecond scale, your volumes to collect many, many volumes of the same brain and construct these time courses of signal in a region, like the three that I've got kind of drawn out, well, that the figure has drawn out on the bottom here. I didn't draw those. But the idea here is you've got this blue line, which is connected to the intraparietal sulcus right here. It's got an arrow pointing to the region. There's also the posterior cingulate in yellow. Do I have a yellow? Sure. So that's this region over here. And then there's also the middle prefrontal, I guess that is, maybe medial. Right there in our orange line. The idea of resting state is if you just collect time courses of signal in a region and assume that to be a proxy for blood flow, what you get is you can do these analysis of regions where blood flow behaves similarly, right? So the yellow and our orange lines overlap quite well between those two regions, implying that they're doing similar things, like blood is flowing to them and neurons are active at the same time. So perhaps they're part of the same network and processing the same information. Whereas the intraparietal sulcus, the blue one, is almost kind of like the opposite of the yellow and orange lines, meaning that those regions are probably not connected. They're doing different things and they're active at different times. So resting state fMRI can give you a sense of kind of networks in the brain that are doing their own thing. Even if they're not active in a task, a network should probably still be behaving similarly even when it's inactive. So just by kind of letting the brain rest and collecting a lot of volumes, you get a sense of where networks are in the brain. And this again requires some kind of intelligent processing and things like component analysis or other nice modeling methods to make sure that you're actually getting a sense of similar blood flow time courses between regions, which usually people talk about in terms of functional connectivity, just regions that are strongly connected in function and doing similar stuff. And you can get some really, really cool stuff out of these studies, which are all the rage at fMRI conferences. Here's just one example of a nice atlas from 2011 that had that identified kind of 7 different principal components in their analysis, and said, okay, these sets of regions belong to 7 different networks, and based on kind of the roles of those regions from previous research, they came up with an explanation. Like the purple network we've got here is the visual network, and we have the somatomotor network or sensory motor network in blue, and so on and so forth. So you can use resting state fMRI to kind of get a sense of the networks of a functional network in the brain, whether you want to parse them in a very large kind of broad way like this study did with 7 regions, or much more fine. There are atlases out there like similar to this one, but they're parcellated into like 400 or 500 regions instead of just maybe the 50 or 100-ish here. You can really get very granular, and there's lots of different options out there for this kind of analysis. And then on the right of this figure, there's also kind of a description of this other related technique called graph theory, where each region of the brain that you're interested in the activity of is represented by a dot, and then the kind of connectivity between these regions is represented by lines or edges in this graph. And then you can kind of visualize which regions of the brain are strongly connected and get a sense of the network architecture of the brain that way as well. So very, very interesting region of research, not my area of expertise, but my understanding, I guess, from the outside is that there's this is kind of the direction of fMRI research moving forward. And also there are a lot of different ways to do it, which is exactly how it is in diffusion-weighted imaging, which is my specialty. There's still tons of debate about what the right parameters for your scans are, what the right processing methods are, but essentially the general concept is let the brain do what it wants, see which regions have similar blood flow, and infer functional networks from there. So that's resting state fMRI. Yeah, I think that was it. The last figure we have is for ASL. Great, so that's my brief coverage of fMRI. Again, anybody who knows fMRI knows this is really just the basics, like I mentioned with diffusion weight imaging. So hopefully you're set up now to kind of understand what you're looking at when you're reading textbooks or digging through articles to learn more about what about fMRI is specifically relevant to you. Last, we have arterial spin labeling. So fMRI was looking at blood flow as a proxy of neuronal activity and looking at kind of change in signal in a region as a sense of kind of where blood was flowing in that region. So that's kind of assessing blood flow in one way, but not really quantifying blood flow, right? That's what arterial spin labeling is setting out to do. Let me just scroll down in my notes here. So ASL aims to actually measure cerebral blood flow generally. This in red. So it's looking to actually quantify how much blood is flowing to a region rather than has the amount of blood flowing into a region changed. And this does not rely on paramagnetic, diamagnetic stuff like I was talking about for fMRI. The concept is actually quite interesting, if you ask me. And to all of your benefit, it requires me to draw a brain, which I am very good at. It's a stubby brain. They exist, I promise. It's got a cerebellum. Use the brainstem here. And got a head outline on my notes, but I'm not sure that anyone wants to see that. So we'll just leave it like this. Assume that there is a skull around this brain. So if you want to look at how much blood is flowing into the cortex, we'll just kind of put the cerebellum to the side. I love the cerebellum, it's amazing, but just to kind of focus on the cortex for now. Just to kind of keep the perfusion distance kind of similar as blood is coming in from your carotid arteries and spreading out to the outsides of your brain through several major arteries. The concept in ASL is to tag the blood flowing into the brain before it gets there, and then image the results essentially. So let me just kind of finish this diagram here. You've got a tagged slice in green. And anyone who does ASL knows this is one way to do ASL, but there are quite a few. It turns out quite a few methods, which we'll talk about a little bit. Okay, so the idea is if we tag some blood as it flows into the brain, kind of like far away from our imaging volume, it actually does need to have some distance. We can't just tag right below, our tagging. Oh, let me draw. Our tagging slice can't be right here because of this phenomenon called magnetization transfer, which I'm not talking about today, but I know about in case anyone has questions. Fairly familiar with it. There needs to be some distance so that the RF pulse used to tag doesn't actually affect our imaging volume at all. But the concept is this tagged blood, which let me explicitly mention is usually a 180-degree pulse. So lots of spins have been kind of incentivized or excited into that anti-parallel state with a tagging RF pulse, and then they're moving into the brain thanks to blood flow and perfusion, right? And then once the tagged blood is in our imaging volume, or really like anywhere, but the effects are of interest in our imaging volume. This tagged blood exchanges its magnetization with other tissue. In our imaging volume. And that again is done through T1 and T2 effects, right? Where spins that have been excited, they just kind of give their energy away to whatever's around them. So this is happening with the tagged blood and surrounding tissue in the brain. And this results in a decrease in available signal. Let me make this present tense. Decreasing available signal. But this is again by 1 to 2%. So similar problem to fMRI, where the change that you're looking for in ASL is quite small. So that, of course, limits your SNR, and you need to account for that, which smart people do. And then once again, we are using the subtraction method to highlight regions where signal has decreased. So that signal decrease is kind of a marker of increased blood flow or increased perfusion to that area. Implying increased perfusion. I've got an animation queued up to kind of visualize this whole process a little bit. And then we'll talk about different types of ASL and wrap up from there, I guess. All right, so we've got a brain, an actual brain, and on the right, there's kind of a model of, you tag blood in the large artery, it spreads out to all these different vascular structures, capillaries, that kind of thing, and you collect two images, one where you're just imaging the brain like we have on the left, and one where you've tagged the blood, and see this decrease in signal, thanks to kind of that exchange of magnetization from your tagged blood to the surrounding tissue. And then if you subtract those two images, you get an image of cerebral blood flow, where, tissue where signal has decreased between those two images. That's where you assume more blood has perfused, or more blood flow is present, I guess. So that's kind of the ASL in a nutshell, is you're using these two different states, just your regular image, and then one where you've actually tagged blood that's flowing into your image of interest, to get a marker of cerebral blood flow. And that kind of gives you a sense of blood volume that is perfused into an area, or the rate of blood flow into an area. Those kinds of questions can be answered by ASL, but not so much by fMRI, where you're just looking at percentage change in response to a stimulus, and not actually like specifically targeting blood with your pulse sequence, and then imaging the results of that blood interacting with your tissue. Okay, we've got a couple minutes left, so let's talk about the different types of ASL that you can do. Initially, people did, or the first technique, I guess, to be developed was continuous ASL. I'm just going to kind of like give a brief oral history of ASL. So continuous ASL, or CASL, it had a kind of constant low energy RF pulse for that tag slice that's marked at the bottom there. And that's what was used to tag blood as it moved through the area. So it's ongoing, which means there's always tagged blood flowing through the brain, rather than just once, like we kind of saw in that animation. But the issue with this technique is that it had high energy deposition. So kind of, there is, with powerful MR, obviously well outside the range of human research or human imaging on modern scanners, but with enough, a more powerful RF pulse, or a long enough RF pulse, there's a chance of tissue kind of heating up over time as energy is deposited into the tissue. And that was an issue for this kind of technique, because there was an RF pulse that was kind of like always on for the minutes of the scan. And also because there's constantly a field being created and constantly power running through both your gradient coils to target that slice that you're tagging, and the actual RF pulse to be generated to make that field. There's kind of high demand on the equipment. And for these main, the main reasons of these drawbacks, the next technique to be developed was pulsed ASL, which is still pretty common, or PASL. And the concept here is you would just tag a little, one slice of blood as it passed through your arteries flowing into the brain. And then you would just image your results and acquire your volume. Typically in 3-dimensional K-space instead of 2-dimensional, so you're acquiring like the whole volume at once instead of just one slice at a time. The good news is that was more efficient. Let me just kind of draw it down. So 1 RF pulse to tag blood. So it was more efficient, which is good. Then efficient than the Castle method. But also because you had less tagged blood flowing through your image, you had lower SNR. And for this reason, we built upon that, not we, but MR physicists built upon that to develop a combination of the two. So pulse continuous ASL. Still, pulsed ASL is used on, I think it's available on GE and Siemens scanners through these sequences called like Epistar and FAIR and things like that. Those exist. They're relevant today, but there's a newer technique that's kind of favored, I think, and the method of choice when available for people who are doing ASL research, and that kind of combines the strength of PASL and CASL. We just finish writing this out. So it's pulse continuous. And then instead of a constant low energy RF field being generated, this one is constant pulses. As if that is an oxymoron. Constant pulses of low magnitude RF or RF fields. And that kind of gets the best of both worlds. It's more efficient in labeling blood than continuous ASL, but also has higher SNR because you're constantly tagging new blood as it flows into the brain, which kind of increases this percentage of signal decrease in your image volume, which means there's bigger contrast when you do that subtraction method to actually image blood flow. Now, the last question I think about ASL is, okay, so we know there's a signal difference and we can use that to infer perfusion or calculate blood flow to an area, but how exactly do we do that? And the answer is, I have ignored equations like this throughout this course, and I will continue to do so now. Blood flow is dependent on a lot of different factors, like the region of tissue that you're in, the specifications of the scanner that you're using, the model that you've chosen to represent blood flow in the brain mathematically. All these different things get added together in a proprietary fashion that differs depending on whether you're on a GE scanner, a Siemens scanner, Philips scanner, all that kind of stuff. So it's more complicated than just saying, okay, now we see this difference in signal and therefore we have this difference in blood flow. This is a refined calculation that people spend their careers developing. Yeah, I was going to say I collaborated with the person that developed this equation. He's a very smart guy. So there are very bright minds behind this kind of stuff, but it is also more complicated than an introductory course would warrant. But that being said, the same kind of drawbacks in fMRI apply to ASL, where you have a low signal to noise ratio, so you kind of have to decrease your resolution, increase your voxel size to make sure you're seeing the blood flow changing your signal and not just noise. And there's multiple different types of ASL available, but the general concept remains that you're tagging blood and watching how signal in your brain changes to get a sense of how blood flow is increasing in that area. But then actually computing the metrics of through blood flow and perfusion rate and things like that, it's a little more complicated than I would like it to be. But that's a general intro for you to DTI, fMRI, and a little bit on ASL. Hopefully that was useful. To those of you that are here, I was given a link to like an actual course evaluation that Realize puts out. So I'm going to put that link here. I suppose I can stop recording, hey? All right.